All right, so last time we ended, right, with seeing that if you take the absolute value of a series and we can prove it converges, then the alternating version of that series will also converge, right? And we said that the absolute value is going to give you the maximum possible sum that that series could ever generate. So if the maximum value converges to S, then clearly alternating back and forth will be even lower sum, and that will go to S, right? So then we said something's conditionally convergent if the alternating version of the series converges, but the absolute value of it does not. And we said, well, the example of that would be the harmonic series. The harmonic series alternates and it converges, but when the harmonic series is positive, 1 over n, it diverges, right? So let's look at some more examples of seeing how to test for absolute convergence. Right, so the first one we want to look at is n factorial over 2 to the n with an alternating term. So if we take the absolute value of this, the absolute value is always going to wipe out the negative term. So all we're going to end up with is this. Well, what do we know about factorials compared to exponentials? Which one's bigger, right? The factorials are bigger. So if the factorial is in the denominator, this thing would probably converge, right? But because the factorial is in the numerator, we actually can say, well, the limit of the nth term, right, as n goes to infinity, is actually infinity, which is not 0. So this thing diverges right out of the gate. We don't even have to apply a test to it. Right? Even if you alternate those terms, they're just going to get really, really big negative, really, really big positive, and they're never going to converge. Well, let's look at this. So if we take the absolute value of this, we're just going to get 1 over the square root of n. And this is a p series where p is a half, and we know that if p is between 0 and 1, or up to equal 1, the p series diverges. So this is not absolutely convergent, right? However, if we apply the alternating series test on the original function, or sorry, series, these aren't functions, right? We can see, well, the conditions are, right, the nth term is positive, so it passes that. The limit of the nth term is 0. And then what's the third condition? What else has to be true? N plus 1 is what? Right, we compare n plus 1 to n, and if the terms are decreasing for all n, then we say we know this thing converges. So if we look at 1 over the square root of n plus 1 and 1 over the square root of n, well, for all values of n, right, from 1 and above, we can see that this denominator is larger than this denominator. They have the same numerator. So this thing is clearly less than or equal to. So the alternating series converges. So this series is conditionally convergent. So it converges the way it is now, but if we try to take the absolute value and look at the positive, it diverges. So one of the things that we can kind of extrapolate from this is, well, we saw 1 over n has this property, right? We saw 1 over the square root of n has this property. So any root in the denominator is going to act this way. So for p series, where the p-value is greater than 0, but less than or equal to 1, they're all going to be conditionally convergent like this, right? The absolute value is going to diverge, but when we take the nth term, they'll be positive. The limits of those p-values will definitely go to 0, and you're going to see that no matter what kind of root you put here, they are going to decrease over time. So these p-series that diverged will pass the alternating series test when they alternate, so they're all conditionally convergent. So that's something, if you can remember, you can cite, right? So you can say, if you're comparing something, you're like, oh, well, this looks like an alternating harmonic series, so I can compare it to that and know that it's going to converge, right? So this is a good thing to have in your back pocket when you're trying to prove these things converge. All right, so let's look at something a little nutty.
Are we applying alternating series test after we've taken the absolute value?
Yeah, so we tested for absolute convergence and it failed. But just because the absolute value converged doesn't mean that the alternating series didn't converge, right? So what we were doing there is we said, well, is it absolutely convergent? Because if it was, we were done, right? But that didn't work. But that doesn't mean the alternating series won't converge. So by the alternating series test, this passed. And so what we can extrapolate from here is that all p series that are divergent become convergent when you alternate them. Okay? So let's look at another one. Right? And remember, I told you that stuff in the numerator and the exponent can be as weird as we want it to be, right? But that number is still going to bounce between -1 and 1. That's all that's going to happen with that -1 term. So here we have -1 to the stuff, right, over 3 to the n. So if we take the absolute value of the nth term, we're just left with this. And that is a form of the geometric series, right? So the series from 1 to infinity of 1 over 3 to the n, that's a geometric series where our r value is 1/3. And since that's less than 1, this converges. So since the absolute value converged, we know the alternating version will also converge. So this series is absolutely convergent. So remember, you only get to state that if the absolute value converged. And so therefore, we don't have to perform the alternating series test on this. So when this test fails, right, for an alternating series, you've still got to apply the alternating series test. But if it passes it, you're done, because it's a pretty easy test to perform. And if you forget to check for this, it's okay. If you just go straight to the alternating series, it's all right. I just want you to see how many options you have when doing this stuff, okay? And if we ask you if something's absolutely convergent, then we're telling you to take the absolute value and test for convergent. And the answer is just going to be yes or no. If the absolute value passes the test, then sure, it's absolutely convergent. If it doesn't pass the test, then it is not absolutely convergent, right? Then if the follow-up question is, well, is it conditionally convergent, then you would have to apply the alternating series test or some other test if that was an option to see if it's actually converging or not, okay? All right, let's look at another one. So a sub n, right, we take the absolute value, is just going to be 1 over ln of n plus 1. So I need to compare this to something, okay, because this isn't like an obvious series, not a p-series, it's not a geometric series, so I need to compare it to something. So, but I do have powers of n at play here. So if you look in the denominator, we have n to the 1. So I actually kind of think this might diverge because the natural log grows to infinity, but it grows to infinity very slowly, okay? And we actually already saw that, 1 over n is a little bit comparable, and n is actually going to grow to infinity faster than natural log will, right? So let's try comparing this to 1 over n, because those are two different series where the denominator grows kind of slowly. So we can do the limit comparison test. So the limit comparison test says take the first one, oops, that's an n, not an a, and divide it by the thing you're comparing it to. So when we divide by a fraction, right, we multiply times the reciprocal. So this is the limit I want to evaluate. This is definitely a L'Hopital situation. We have infinity over infinity. So I'm going to take the derivative of the numerator, which is just 1, and the derivative of the denominator is 1 over n plus 1. So when I flip this fraction and multiply times the reciprocal, I'm taking the limit of this. And this limit is infinity. So when you're doing the limit comparison test and you're testing for divergence, okay, if the limit comes out to be infinity, you can conclude that the series also diverges, right? If the limit is greater than 0 in a real number, then we know that they behave the same way, and they actually behave very closely together. But in this case, what's going to happen is n is just, when you end up getting infinity, we can also conclude that the series diverges. So this guy is going to diverge, so that means the original series was not absolutely convergent, okay? So all we know now is it's not absolutely convergent. That doesn't mean that that thing might not converge as well, okay? So to test for convergence, we're going to have to apply the alternating series test. So if we look at the alternating series test, well, our a sub n is 1 over ln of n plus 1. That's positive, so it passes the first test. Then the limit as n goes to infinity of that term goes to 0, so it passes that condition. Then we need to check, well, are the terms decreasing? So 1 over the natural log of n plus 2, how does that compare to 1 over the natural log of n plus 1? So since the natural log increases over time, right, as x goes to infinity, it goes to infinity. And remember, the graph of the natural log of x looks like this. So, right, so as the values inside get bigger, this is just going to infinity very slowly. So clearly this denominator is larger than this one, which means this guy is in fact less than or equal. So this series is conditionally convergent. So it kind of makes sense when we compared it to 1 over n, it performed, right, in the same way as a harmonic series. When it was positive, we got that it was divergent. So it makes sense that it would converge when it alternates, just like the harmonic series does. Are there any questions on this? So if you test for absolute convergence and it converges, you're done. If it fails absolute convergence, you still have to apply the alternating series test. Okay? All right. Any other questions on that? No? All right. So I'm going to show you something fun. I told you guys way back at the beginning when we started sequences that what made a sequence was that was a list of ordered terms, right? And they had a well-defined pattern. So that's why we can use an equation to find those order. And I said, you guys are going to forget when we get knee deep in the woods that not only when we do series, the sequence has to be generated in a specific order, but when we're doing a series, the numbers you're adding together are being generated in a specific order. So here's what's a little mind-blowing. If I want to add A plus B, well, I'm allowed to switch that and say B plus A. They're equal, right? So if you are adding a finite number of things together, you can rearrange the order of those things in any way you want, and you'll always come out to the same sum, right? But what happens if we rearrange an infinite list of things together, right? So this is where I was telling you guys, the order in which this thing is generated matters, right? So let's look at what happens if we mess with the order. What does that do to the sum? So if we take the alternating harmonic series and we list out the first couple of terms. So a little bit later, I'll circle back to this and I'll show you why this thing is going to sum to what it does. But we know from like testing the remainder and getting a range of the sum that when you sum this series up all the way to infinity, it works out to be approximately equal to the natural log of 2. So now, let's rearrange these terms. So I'm going to keep 1 over 1 minus a half. We're going to keep that up front. But then, I'm going to skip 1 over 3, and I'm going to jump over here and take 1 over 4. And then, I'm going to grab 1 over 3 and subtract 1 over 6. And then I'm going to do 1 over 8. So what I'm doing here is I'm taking a term and I'm subtracting the term where the denominator is twice as big. Okay? So 2 times 1 is 2, 2 times 3 is 6, right? So I'm grabbing all the odd terms and then I'm immediately subtracting the term that has twice the denominator. Then I'm backfilling with the even terms that I was skipping along the way. So the next one, if I kept going, right, we've grabbed 1, 3, so then I'm going to grab 5, and then I'm going to subtract 10. Then I'm going to simplify what's in those parentheses. So 1 minus 1/2 is 1/2, so then we still have 1/4. 1 over 3 minus 6 is 1/6. We still have 1/8. 1 minus 5, or 1 over 5 minus 10 is, oops, sorry, I'm not adding right. These should be positive. I'm going to get 1/10. So now what I'm creating is an alternating series where all the denominators are even. 2, 4, 6, 8, 10. That's what this did by rearranging them. So since all the denominators are even, I can factor a 1/2 out front. I can take a 2 out of every denominator. So then, let's pull a 1/2 out front. And now I'm left with this. And that will go on all the way to infinity. So look what's in the parentheses now. It's the original series. So we know that when you take these terms and sum them in this order, it's equal to about natural log of 2. So the sum of the rearrangement is 1/2 of natural log of 2. So what we did was we shoved smaller terms to the front when we did this rearrangement. So we slowed down the growth that it was counting to infinity. And as a matter of fact, we cut it in half. So when you're summing up an infinite number of terms, the order you're summing in matters. So that just kind of violates this like basic mathematical principle that you guys learned in like elementary school, that you can add 2 and 1 or 1 and 2. But what you didn't realize is that only applies to a finite list of things. So these series, if we adjust them or violate the order or change the pattern, we're actually going to change the sum, right? So I'm not going to expect you guys to be able to regurgitate something like this. I just think it's a really neat thing to see. And you're like, what the hell are we doing? Why does this matter? And why do I have to be so careful with everything I'm doing? Because if you change something that you're not allowed to change, you've changed everything, okay? So changing the order can change the sum. And does it make sense to everybody why the sum reduced because of the way we changed the order? If I had shoved some of the bigger terms to the front, we might have been able to increase the order of the sum of the series, right? So it's not just that we're adding, but one of the reasons we keep using limits is we're calculating like the rates that things are getting to infinity, the rates that they're going to 0. And so if you change the speed, you're going to change the sum, right? Make sense? Okay. So that's the end of this section. And the next section is 9.5. We're going to go back a tick, right? So a lot of people like 9.5, right? I like 9.5. So that's the ratio and the root test. And anytime we can apply those, they're actually quite useful. And this is where you got to be really good at your exponential math.